No? Okay. So, good morning, everyone. Or afternoon, whatever, I don't know. For me, it's morning. You might have realized that. It's, in fact, a little below my threshold, but okay. You may wonder about the title. You'll understand it at the end of the lecture, I hope. Okay? So, let me start immediately. We are going to talk about a very, very simple problem. Okay? Extremely simple. We have one seller, and we have one buyer. Okay? Okay. We may have more than one good. We have K goods, okay, or items. Okay? And the objective, very simple. The seller wants to maximize his revenue. Okay? Very good. Classical problem, very simple, very natural. Now, let's put some flesh into the problem. So the buyer evaluates the goods. Let's call that x1, x2 up to xk. So those are the values of good 1, good 2, and good k. And let's assume the simplest possible model. As I said, it's going to be complicated enough. So we want to start as simple as possible. Then you can expand it. Okay? Value is additive, which means if the buyer gets both good 1 and good 2, it's worth to him x1 plus x2. Okay? Now, the buyer knows exactly what x, the vector x is, so he knows exactly how much he values each one of the k goods. The seller does not know that. Okay, sorry. Let's assume the seller knows that. Then lecture is finished, right? I can go home. I mean, you save an hour and a half or an hour and 20, an hour and a half minus epsilon, because then the seller is going to say you can get good 1 for x1 or x1 minus epsilon, you know. Good 2 for x2 minus epsilon, and that's it. So the whole issue is that the seller does not know the value of does not know x, does not know the valuation of the buyer. What he has a belief, as usual, on this valuation. So we're assuming that x is distributed according to some probability distribution, let's say CDF script f on RK plus. So values are non-negative. It's hidden here in this assumption. Think of this f as the belief of the seller on the valuations of the buyer, or if you want, how the valuations of the buyer are being drawn out. Okay? So the seller knows f. So think of x as a random variable. If that scares you, doesn't. I haven't said anything, but just for some notations. Now, just to put things aside, not to worry about them, both the seller and buyer have quasi-linear utilities, which means that they are additive in money. And they are risk neutral, which means that getting a good worth 7 with probability a half, it's worth to them 3.5. And if they have to pay for this 2, it's worth to them 3.5 minus 2, which is 1.5. That's how you make computations, as simple as that. Okay? By the way, probabilities, in this model, one can think alternatively of probabilities. So you can get a good with a certain probability, or if it is an item which is indivisible, or you can get a certain proportion of the goods, so that could be a quantity. Okay, so Q is going to be probability or quantity or whatever. Okay, now let's make another simplifying assumption. The seller has no value for the goods, so keeping the goods gives him nothing. There's no cost in producing the goods. As simple as that, the most basic model possible. Okay, so again, remember the objective, maximize revenue. Very good. So let's start with one good, k equals 1. So that has been solved by Roger Meyerson, 1981. Well, much more complex problem than this, but that's included there. And it says the following. So also Riley Samuelson. I guess there probably for this special case, there may probably other people may have said what is going to be on this slide. Wiley Zackhauser, right. So Riley, right. Okay. Okay. Right, you mentioned that in your talk. Okay. So, very simple. The seller posts the price P and then gives the buyer a choice. Either you pay P and get the good, or you pay nothing and get nothing. Okay? You choose. Okay? How is P chosen? Well, P is chosen in such a way that the revenue is maximal among all those possible mechanisms, which means that if he posted the price P, he's going to sell provided that X is bigger than P. Remember, X is now just one real variable. And so if the valuation is bigger than P, then the buyer is going to get the good. because remember, he gets x and pays p, so he gets x minus p. And now this is just 1 minus fp, so we just maximize this expression over p. So for example, just to warm up, if x is uniform on 0, 1, price is a number between 0 and 1. Clearly, charging a price of 2, you're never going to sell anything. So price is going to be between 0 and 1. If you charge price p, you are going to sell provided the value is bigger than p, which is probability 1 minus p. So you maximize p times 1 minus p, which even at this hour you can easily compute to be p equals a half, optimum, and revenue a quarter. Okay? So that's the kind of computation we do. Very good. Okay? By the way, proving this theory, okay, sorry. Now, what Meyerson proves is that this is an optimal mechanism. Okay? There may be more, the P need not be unique, but one of these is for sure optimal. Okay? That's not a trivial result. In fact, I may give you a couple of proofs along the way, but if you try to prove it from scratch, it's not easy at all. Okay, now, you prove it, I know. I'm saying for people that haven't been at this summer school or haven't have had any serious education in this matter, of course. But I'll give different proofs then. Okay. So let's take an example. X takes the values 10 and 22 with equal probabilities. So clearly, putting a price of 12 makes no sense, because you are going to sell at 12 just as exactly the same case when you sell it for 13, in fact for 22, or 22 minus epsilon. We are ignoring epsilons. So price clearly is going to be either 10 or 22. Makes no sense to put any other price. If you put price of 10, you sell for sure, and you get a revenue of 10. And if you as a seller set the price at 22, you are going to sell, provided the value is 22, which happens to probability half. So you get 22 is probability half, which is 11. 11 is bigger than 10. Numbers have been carefully chosen. And so that's the optimal revenue. Okay? Very good. Now two goods. Okay, we've done 1, 2, you know, we have a few, we have an hour, we can go 2, 3, and so on. So let's go to two goods now. So let's assume they are independent. Okay? What does it mean independent? So x1, the value of good 1, and x2, the value of good 2, are independent, which means even if you know the value of good 1, it tells you nothing about the value of good 2. Okay? They're really independent goods in any sense you want. So I mean, if we take Meyerson's result, it says, well, let's put a price P1 to good 1, and price P2 for good 2, whatever is the right price for the two goods, and see what we get. Okay? So let's take an example. Let's assume now that x1 and x2 are the same as the previous x, which means independent and identically distributed, taking values 10 and 22 with equal probabilities. Okay? So we already know that the best you can do is to set a price of 22 and get revenue of 11 for good 1 and get revenue of 11 for good 2. Right? That's what we computed, which gives you a total revenue. That's a computation. That's a maximization. So total revenue is 22. Okay? And now we are very happy, and especially if you have never seen anything like that, you are very happy and go home, but you are going to lose money if you are a seller, because it turns out you as a seller can do something better. And what is that better? That thing that is better is to come to the buyer and tell him, look, you cannot buy the goods separately. You tie them in a bundle, you know, put a nice ribbon among them. Here are the two goods. Okay? You pay 32, you get both. You don't pay anything, you don't pay 32, you get nothing. Why is this good? Now, what's 32? It's 10 plus 22. So if you value both goods at 10, clearly you are not going to pay, then the two goods are 20, you are not going to pay 32. Any other case, you value the two goods at 32 or maybe even at 44, so you are going to buy with probability 3/4, and 3/4 times 32 is 24, which is bigger than 22. Okay? Now, again, as I say, probably for you guys this is not a surprise, but anybody who sees that immediately says, well, where am I cheating? Yes, I have to roll off my sleeves and show that I have nothing hidden my sleeves, do the computation again. Nobody believes it at the beginning, yes? Now, why is it? Let me try to give an explanation, okay? Well, the reason, why is it that the seller is not getting the value of the good from the buyer? Why can't he charge him what the buyer values the good? Because he doesn't know what the buyer values the good. And if he's going to ask the buyer, how much is it worth to you? Oh, nothing, you know, I don't care about this good. Of course, what is he going to say? It's worth to me 22? Of course not. So that's the price, or that's the cost of the seller of his ignorance, of the fact that he doesn't know the valuation. Now, when we put the two goods together, okay, the uncertainty of the seller in a sense, is lower because we add things. So uncertainty, it's like a law of large numbers, but in a mini law of large numbers. When we put them together, there is less uncertainty, and that's why you can do a little better. Okay? I think that's a very good explanation, except it's false. Okay? And I'll show you in a minute why it's false. But it's a very good explanation, I think. I like it. Okay? But, you know, it's not right. But has a smack of truth. In fact, it's true if we have 100 goods, it's correct. Okay? If we have 100 IID goods, like this, okay, then 100 being a large number. I think 1,000 if you want, okay? 1,000 IID goods like this, what I said is perfectly correct. Because then when you look at the sum of all goods, of the sum of the 1,000 goods, well, the average of the goods is 16. 10 plus 22 over 2, yes? So 1,000 such goods are going to be worth to you 16,000 plus minus a little error that comes from the, you know, you can estimate it central limit theorem, but it's more or less worth 16,000 plus minus something. So I'm going to charge 15,900. With very high probability, the valuation of the sum is going to be above that, and then I'm going to get my $16 per good, which is the most I can get here. Okay? So that expression is true when I have many goods. It's not true when I have 2 goods. Okay. So now, okay, general mechanism, I don't know. I mean, again, this lecture, I give it to various, to people who never know mechanism design like me. Yes, I really don't know mechanism design. I'm a newcomer. But, you know, so I start from the beginning. So I think I can skip, can do this quickly. But so, okay, you know what? That's good for introducing some notations. So what's an outcome? What do you care about? What's going to happen? Well, let Qi be the probability that the buyer gets good I. And now it's important to understand that Q, which is a vector Q1 up to Qk, all these numbers could be 1. So there is no restriction that you only want one good. There are other models which are called unit demand, which is a parallel analysis. Sometimes it's easy, sometimes it's different, sometimes it's they are not the same. There you assume that the sum of the q's is 1. So here we do not assume that the sum of the q's is 1. It's not in the simplex, it's in the cube. Okay, so all the q's could be 1. You could get all the goods. Like before you got both goods. And then S is going to be the payment from the buyer to the seller. So think of S, what the seller gets. That's why I'm using the letter S. And then what does the buyer get, which I'm going to denote by B. Everybody here in this area uses, all letters of the alphabet have been used here for everything, more or less, which when we started working, by the way, most of what I'm going to talk about is work with Phil Rennie and with Noam Nissan. I'll mention whenever I come to something that we did. But for 1 year, I was completely confused about, you know, oh, that's what the seller gets. No, that's what the buyer gets, because that's an X. No, that's a P. That's an S. That's a... So at least now, S is what the seller gets, the utility of the seller. B is what the buyer gets. That's now I remember. So what does the buyer get? Well, he gets good X1 is probability Q1. Remember, risk neutrality and additivity. So that's his expected payoff minus the money that he has to pay, S, which is what the seller gets. So that's B. Okay. Now, what's a simple mechanism? Let me describe a simple mechanism. Here is a very simple mechanism. There is a menu. What's a menu? It's a set of possible outcomes. Yes, like you go in a restaurant, you get a menu, and it tells you, look, you can get good 1 with probability half, good 2 with probability 3/4, and good 3 with probability 1, and you pay 17. That's one option. That's menu 1. Like they call it menu, but it's really an entry in the menu. Okay, the menu is the big thing. But you know, when you go to a restaurant, in the big thing, which is called the menu, then you have small things that are called also menu. Yes, special menu 1, special menu 2, and so on. We are going to call them entries in the menu. Okay. Then another thing says, you know, you can get good 1, pay 7, or you can get good 2 with probability 3/4, and good 7, and you pay 12. Choose. Okay. So you know, like everybody in a restaurant, you look at it and start scratching your head, and you choose one or another. So that's a menu. It's a set of possible outcomes. The seller now posts such a menu. And what the buyer does, he chooses one of the outcomes in this menu. Okay? Let's denote by Q of X, S of X, the outcome that the buyer chooses when his valuation is X. So X is a vector, remember? When his valuation is X, he chooses, we'll see in a moment how, one of the possible outcomes here, which gives probabilities of getting the goods and payment to the seller. Okay?
All mechanisms are like this?
Wait. Well, the bottom line on this slide is for you. Okay? There will be a revelation for you. You should wait. Okay? So the payoff of the seller is S of x, and the payoff of the buyer is what? When his valuation is x, he gets x with probabilities qx, so we take the scalar product, and you subtract S of x. Very simple. Now let's call this a menu mechanism. And now we come to the revelation principle, which, again, don't think it comes from Mount Sinai. It essentially says that the game in extensive form can be represented in strategic form. That's all it says. It's really that. Okay? Nevertheless, it's an extremely useful tool. But that's what it is, yes? It's not any deep mathematical result. And what it says, every mechanism is equivalent to such a mechanism. Okay? You just represent it in strategic form. All you care about the outcomes. You don't care how they get to these outcomes, yes? You don't care what the mechanism exactly is. Okay. And that's, if you want, is a direct mechanism, what I described here for the connoisseurs. Okay. Now, the buyer, what are the constraints of the buyer? Incentive compatibility that says, in particular, it says that whatever he chooses, which gives him that, when he is at x, he chooses the menu item corresponding to q1x, qkx, and s of x. That's the payoff that the buyer gets. It should be better than anything else than the menu item that he gets when his valuation is y. It should be also better than other menu items that maybe he never chooses them, but we ignore those things. But for sure, it must be that when his valuation is x1 up to xk, he prefers getting what he's choosing to any other thing that he could have chosen, in particular, that menu item that y chooses. So this inequality surely must be satisfied for every x and y. Notice those things, x, y, xy, but here is the true x. That's called incentive compatibility. And we also have the participation or individual rationality constraint that just says, well, you can always stay out, and let's assume that the outside option is 0, so it should be that payoffs are non-negative. Okay. What about the seller? He wants to maximize revenue, remember. So what does he want to maximize? What he's going to get from valuation x is S of x. So you take the expectation of S of x, you know, depending if you come from probability, you like E. If you come from analysis, you like integrals, you know, it's the same thing. So I wrote them both. Of course, subject to the fact that Q and S satisfy the constraint on the previous slide. So far, so good. Now, let's look at the incentive compatibility. I claim that from that, you can immediately see that the function B, which you remember is the payoff function of the buyer. So B of x is what the buyer gets when his valuation is x, is a convex function of x. Okay? Now, that's a very complicated result. Here is the proof. Okay? Look at this function. That is what he's going to get when his value is x, and he uses the menu item for y. Now, this thing is the linear function in x. Now, mathematicians call it affine because it's not 0 at 0. But for everybody else, it's a linear function. For economists, it's a linear function. Okay? What is b of x? Well, it's the maximum of that over all possible y's. So it's a maximum of linear functions. So if you take linear functions and you take the maximum, it's a convex function. End of proof. Okay? That's it. It's all very straight. Nothing else. Okay. Now, let's do something a little more advanced. Econ 0, 0, 0 plus epsilon. Because b of x is qx times x, then q of x is the derivative or the gradient of b with respect to x. Okay? So here is an intuitive proof. Suppose that your valuation for good 1 increases by epsilon. Now, essentially, the optimum, so let's assume we're on a nice wall just to get some intuition, or if you want, it's the first order conditions that say that envelope theorem, whichever way you want to say. Essentially, you are still going to use the same menu item. So by how much is the buyer's payoff going to increase? His valuation now is, instead of x1 plus epsilon. He's using the same menu item, up to second order effects, of course. So he's going to get the good x1 plus epsilon with the same probability. So you're going to get q1 times epsilon times x1 plus epsilon, which means an addition of q1 times epsilon. We divide by epsilon, it means the derivative is q1. So derivative of b with this, of the payoff to the buyer with respect to the first variable is exactly the probability of getting the good number 1. And that's true for every good. So that says that the derivatives of b are exactly the q's. Okay? As I said, again, you can use whatever your favorite way of proving such theorems, but you have all seen zillions of those. And okay, it says it here that qi is the derivative of b with respect to xi. Now, of course, who says b is the differentiable? Well, convex functions are nice, and they're almost everywhere differentiable, so that's good. And almost everywhere is good enough, as you'll see. Okay, now look at this equation. B of x is the gradient of b times x minus s. I'm going to do now a very significant manipulation and move b and from one side to the other. So s is the gradient of b times x minus b. Okay, let's put this up. So, so now I can restate the problem as follows. B is a convex function. So let's look at all the functions defined on the non-negative orthant, which is where valuations lie. Remember, I said valuations are non-negative. So I have a convex function defined on Rk plus, R2 plus, yes, for now. Convex functions, I said. The derivatives, remember, are the probabilities of getting the goods, so they better be between 0 and 1, yes? As I say, if you when I teach probability, I used to teach probability, I said, you know, if your probability comes negative, that's not the right answer, it's your grade. Nevertheless, you'll be surprised how many times they do computation, they get minus 0.1, or for the variance, you know. Okay. Yes, no, it happens. And they never say anything, you know, okay, minus 0.1. Some are smart enough to say, well, I made some error in the computation. Okay, that's good enough. Okay, never mind. So, also, you can assume b of 0 is 0. That's without loss of generality. Let's not get into that. Otherwise, you lose money. And so, let's look at this expression. What is this? This is the revenue that you get from the function b. So, what's nice here is that the function b, which is the payoff function of the buyer, determines exactly how much the seller is getting. This is how much the seller is getting. Remember, that's s of x. So, this is the expectation of s of x. Yes, look at this previous slide. This is s of x. So we have expressed the payoff of the seller in terms of the payoff of the buyer. Okay? So we get this nice expression.
Can you say anything about s of x? Is it convex, concave?
Neither.
Okay.
I said a lot of things. Yes, but I can say lots of things about that, but not now.
So
I can tell you lots of things. Yes, because it's again it comes from a convex function and it has this expression. Okay. Right. But of course, it's equivalent. It's just a matter of convenience. But you'll see now why it's a convenient convenience. Okay. The reason it's a convenient convenience because look at this expression. This expression. Okay. By the way, there is here. This is defined almost everywhere. So if you want to get rid of, sometimes people use one page to get rid of the almost everyone improves. Approximations and so on, so on. That's crazy. No, you should use directional derivatives. Then you don't need to do anything. Okay. Reference Hart and Rennie 2015. Some footnote there will explain how to do that. That saves pages in some proofs. Well, it's just a technical convenience, nothing else. Okay. What's a revenue? It's to maximize this expression over all possible functions b here. Okay. I haven't proved to you that every function b can be interpreted as a mechanism. But it's very easy. Give me a function b with derivatives between 0 and 1. Let me define q to be those derivatives, and that's what remains. It's a mechanism. So that's very easy. Now, why is it a useful representation? Because this set of functions is a closed set. Okay, we don't care about that. It's a convex set. Why is it a convex set? Averages of convex functions are convex functions. Average of functions whose derivatives are between 0 and 1 have derivatives between 0 and 1, because average of derivatives is the derivative of the average. Right? Averages of functions that are 0 and 0 are 0 at 0. So this set is a convex set. So, and also it's a closed set, but that's technical. We don't care about that so much. This expression is linear in B. If I take now, yes?
So what if I set of functions that a k is convex, right?
Sorry?
You say the set of functions.
Yes, the set script bk is a convex set, which means take b1 in this set, take b2 in this set, take their average, pointwise average. It's going to be in this set. That's what I say. Okay? So half b1 plus half b2, pointwise, at every x you define it this way, where half is any number between 0 and 1, of course, is going to be in this set. Okay? And why is it good? Because look at this expression. This expression is linear in B. If you take half b1 plus half b2, just a second, let me finish, then derivatives, okay, the derivative of half b1 plus half b2 is half the derivative of b1 plus half the derivative of b2. So this is going to be half whatever you get for b1 plus half what you get for b2. This is the same. So this expression for half b1 plus half b2 is half the expression for b1 plus half the expression of b2.
I hate to be this guy, but why is the set closed? And
That's an easy exercise, which is technical and doesn't really matter. You look at the limit, pointwise convergence. For convex functions, it's very easy. Convex functions, bounded derivatives, there is no problem, whatever you want to use. Any topology. Yes, but you look at the natural pointwise convergence or any infinity convergence, whatever you want, doesn't matter. And that's, but that's not important, again. If it's not, take the closure, okay? You know what? Take the closure of BK. Work with that, okay? And then you prove in a lemma it's the same as BK, but I'm not using that. What's important is that I'm maximizing a linear function on a convex set. Now, the fact that this convex set is not in the plane, but in the space of functions, that doesn't matter. When you maximize a convex function, you maximize a convex function over a convex set, you know that there is a solution at an extreme point. Okay? So, let's find what the extreme points are. If we find the extreme points of that set BK, then we know that at one of them we'll find an optimal mechanism. Optimal, I mean maximizing revenue. Okay, so the revenue is the maximum of all extreme points of BK of this expression. Okay, very good. By the way, this is Manelli and Vincent. They wrote two papers, very, very nice. I think that may be the second one. 2006, 2007. Then there is a correction on 2012 on one of the results. It's a side result, but anyway, you may want to check on that. Okay, let's go to one good. Special case one good. So one good, what I do, all the cases become one, and derivatives now are derivatives, as you are usually right, with just one prime. Okay? Huh? One can't argue with that.
It's a derivative, it's difficult to argue.
Yes, yes. Okay. So now I'm looking at this. So what is B1? Okay. Make a picture. Okay. So this is x. Now I have just one variable. Okay. And I'm looking at functions that start at 0, are convex, and the slope is always greater or equal 1. Slope. Okay. You can see clearly that's a convex set. Averages of such creatures are, again, such a creature. What are the extreme points? Okay? Okay, now it's an easy exercise, especially if you know the answer. I'll give you the answer. The extreme points are functions that look like this. You take here a point P, and you take derivative to be 0 up to that, and then derivative to be 1 from then on. So that's slope 1, slope 1, and here is 0. Okay? Exercise for you. I'll give you no more than 5 minutes after the talk, not now, to prove that every convex function's derivatives between 0 and 1 can be expressed as an average, maybe as an integral average, of functions that look like this, that have slope 0 and then 1. Okay?
So what do you mean by extreme points? Points that every other is an average?
Exactly. Okay? Exactly. Now, conclusion. So if you believe this statement, which again, as I said, it's not difficult to prove, but, 3 minutes I give you. No, 5 is too much. 5 is too much, especially since you know the result, yes. Now, what is this function? Okay, this function, by the way, I'll write it this way. It's x minus p plus, which means if x minus p is negative, you put 0. If x minus p is positive, it's x minus p. What is this function b? Remember, what we draw here is b of x, is the payoff to the buyer. So that says the buyer gets x minus p, the maximum between x minus p and 0. What is this? That's exactly what the buyer gets from the mechanism where the posted price is p. Because if his value is below p, he gets 0. If his value is above p, he pays p and gets x, net x minus p. So that's exactly the Meyerson mechanism for posted price p. So we've proved Meyerson's result, because we said those are the extreme points. I know that at one of those, the maximum is attained. So optimal mechanism is a posted price mechanism. Okay? I think that's a very nice proof. Okay, which is, by the way, here. By the way, you can find this presentation on my webpage if you want to look at that later. And okay.
We'll also post this on the summer school.
Okay, I can probably, or probably it's going to be posted one way or another. Not just the price, also the presentation. So you have a posted price presentation or something. Posted. Yeah. Okay, now, so far so good. We work for one good, so let's go to two goods, let's say. Okay, so two goods. We have the plane. Think of it. Here is the plane, the non-negative Horton. Okay, no, I hasn't. So Jason, okay. You have a convex function that starts at 0, it's 0. Here is 0. Okay. The derivative in both directions are bounded. So it's greater or equal 0, which means the function is monotonic. Okay. And it's convex, so derivatives always go up. They never go above 1. Okay. What are the extreme points of of the collection of those convex functions on the non-negative Horton with derivatives between 0 and 1? Okay, so there'll be things like, you can go like this and then slope 0 and then slope 1, and you can do it in different angles and so on. Now, those are extreme points indeed, but they are very, very far from exhausting all extreme points. It turns out that extreme points here are wild. You can get functions. So first of all, you have functions where derivatives are neither 0 nor 1. I mean, you get anything in the middle, including irrational numbers, including boundaries that are not linear. They can have crazy equations and so on. The collection of extreme points here is wild. Nobody knows how to characterize it in any useful way. In fact, I am going to go out on a limb, on a very strong limb, in saying there is no useful and beautiful characterization, like in the one-dimensional case, of the set of extreme functions. Okay? So it looks like an easy problem, and every mathematician, when he hears that, says, oh, sure, I can, give me a day, I'll do that. But, many mathematicians are given more than one day and still there is no good answer. My suspicion, there is no good characterization here. Okay, so what we have is something very nice but useless, because the extreme points are extremely complex. We have no useful characterization of them, so we cannot say optimal mechanism has this shape or another. Okay, so we can now go home. No, still I have still 1 hour, less than 1 hour, so not yet. So let's look at a few more examples, and then let's see where we go from here. So let's go back to this example. Big change of notation. X1 and X2 are now Y and Z. Indices tend to get lost, so now let's call them Y and Z. So Y and Z are the two goods. Remember, if the two goods were worth 10 or 22 with equal probabilities half-half, then if you sell them separately, you get the revenue from Y plus the revenue from Z, which was 22, 11 from each. If you sell them as a bundle, what are you really selling? What is it? The value of the bundle. The value of the bundle is Y plus Z. It's a random variable Y plus Z. That's how much it is worth. So again, to find out what's the optimal way to sell it as a bundle, you apply the Meyerson mechanism, Meyerson, Riley, whatever, big list of names. But everybody calls it the Meyerson mechanism, so I'll keep saying it. Yeah, the posted price mechanism, I'll say.
That's the problem.
Yeah, I know.
The other guys always get left out.
Okay, so I'll say the posted mechanism, the posted price mechanism. Well, Roger's claim to fame is not from that. It's from the other things, but never mind. But, what people remember is the simple things. It's okay. You just look at the revenue of Y plus Z. Y plus Z is a random variable. It takes 3 possible values. You can compute what the optimum thing is, and it's exactly what I told you, is to put the price of 32 when you sell with probability 3/4. Okay, so far so good. I'm just repeating what I did. Okay? Very good. Now, so here, the optimal mechanism is to put a price on the bundle. Good. Now, let's make Y and Z 10 and 50 with probability half-half. What happens then? Well, if you sell it separately, price 10 gives you 10, price 50 gives you 25, because you sell with probability half. So clearly, price is 50, and then you get 25 for each good, which is 50 in total. Everybody follows, or I hope so. It's not too difficult. When it's going to be difficult, I'll tell you. But for now, I can say it even. If you do it bundle, okay, you have to look at the different, the value of the bundle is 20 or 60 or 100 with those probabilities. The best that you can do here is the price of 60, set probability 3/4, you get 45. 45 is less than 50. So the best thing here is to sell separately. So there goes by the window my explanation that when you put the two goods together, there is less uncertainty, and that's why bundling is good. Because that has nothing to do with the values. That explanation has nothing to do with the values. It has to do with information. That's why I said that that explanation that there is less uncertainty on the bundle, that's false, because if it would apply, it should apply here also. So it's a much more intricate relation between values and probabilities. It's not just something that talks about information. Okay? So that's first thing that we learn from here. Okay, so here you price each good separately. Okay, good. Example 3. Okay, 0, 1, 2, 3 values with equal probabilities 1/3 each. IID, 2 such goods, IID. Okay? Okay, here you have to believe me, but not much. You can do it in 2 minutes, all these computations. If you sell it separately, you can put a price of 1, and then you sell with probability 2/3, when the value is 1 or 2, or a price of 2, and then you sell with probability 1/3, both of them giving you a revenue of 2/3. So from both goods, you get 4/3. If you sell them as a bundle, well, there are a few more possibilities. Believe me that you get 4/3 also. This example was very carefully chosen, despite the fact that all the numbers look completely generic, 0, 1, 2, and 1/3, but they have this nice property. So selling separately gives you 4/3, selling bundle gets you 4/3. That's it, right? Wrong.
No matter how you make the bundles,
What do you mean? You have two goods. What do you mean? How can you make the bundle with two goods? It's either one good, first good, second good, or both of them. No other bundle. There is no chocolate on top that you can add. That's out of the model or something. Okay, wait. So, as I say, selling separately, so 4/3, bundled 4/3, so we go home, right? No, wait, don't go home. There is something else we can do, which is, I'm going to write it just to start, to have you start to get used to this. This is the value, this is the payoff to the buyer. When his valuation is YZ, it's a maximum of 4 things, which I read it as follows. Here are the menu items from which the buyer can choose. He can choose to get 0 by just going home. He can always get 0. He can get Y minus 2. How does he get Y minus 2? He gets good 1, which is the Y good, which is worth to him Y, and pays 2. So that says pay 2 and get good Y. Or pay 2 and get good Z. That's another choice. Or pay 3 and get both, get the bundle. So that's how we read this. From this, you can read exactly the menu that he faces. Okay? Now, if we compute the revenue here, you can compute the revenue exercise, not very difficult. What you get is 13/9. Now, what's important about 13/9 is that it's 1/9 bigger than 12/9, which is 4/3. Okay? That's a crucial property of 13/9. Nothing else matters. Okay? Okay? So here, in fact, it's a unique optimal mechanism. One can show this easily. By the way, for discrete distribution, it's just a linear programming problem, so there is no problem to compute optimal mechanisms. And so here, the choice that is given to the buyer, there is a price on each good separately and the price on the bundle, and the buyer, according to his valuation, chooses what to do. Okay? It's a more complex mechanism than separate, selling, or bundle. Okay? Okay. Can we go home? Wait. Okay. Example 4. Okay? So now it's going to be easier to explain if I have a joint distribution. They are not independent, but there is an example for prime that I will not explain, but you'll see it, where things are IID. So this has nothing to do with correlated values, but it's easier to explain here. So assume that the value of the two goods, the valuation of the two goods for the buyer, can be one of 3 things with equal probability. Either he likes good 1 at 1, the Y good at 1, and doesn't care about good 2, or he values the second good Z at 2, but not the first good, or he values both goods at 3. Okay? That's the situation. So I claim that the thing that is written here is the unique optimal mechanism. Okay? Now let's read what is written here. Okay? Ignore for the moment the red and the red and yellow and so on. I'll read it as if there is nothing there, but that of course stares you in the face. Okay? So we'll see in a moment. That says, what is the choice of the buyer? Nothing. That's always a choice. Let's jump over this crazy thing. Pay 2 and get the second good. Good. Pay 5, get both. Very good. Half Y minus a half. It says, you pay me $50 and you are going to get a lottery ticket that is going to get you good Y with probability half. Come on. I mean, we already argued everything is linear here. I mean, why should you use probabilities? Okay? So instead of doing, and that gives you revenue 2.5. One can easily compute. Okay? And it's a unique optimal mechanism, I claim. And you are going to say, no way. right? That's what I will say.
How do you find this B if it's optimal?
It's, as I said, it's a linear programming problem, okay? So that's how you show that it's optimal, or 10 different ways you can do it, but that's, as I said, that's not what's important. So what is this half y minus a half? So instead of getting, yes?
Sorry, I'm wondering why is it a 5 for the case that y will goes 1?
Because that's what comes out. What do you mean why it's a 5? Why and if it would be a 7, you'd ask why it's a 7.
Instead of 6.
No, Sergio, because it's 3, you have 3 plus 2, you can explain it.
I mean, of course, it depends on the valuations.
What's the
Yes.
question?
I mean, this is not arbitrary. It's the optimal mechanism for this specific distribution. That's what I'm claiming. Yes. So you compute and that comes out. But in a moment, I'll give you a much better answer. Okay. Why 5? In fact, I'm going to.
This needs to be 5 because if you don't give it for 5, then the buyer will buy Z for 2.
Yes, but that's assuming that the other things are correct. So you are proving one thing depending on another thing that I haven't proved, and that other thing you prove. So okay, that's not a proof. But okay, but all this. Wait a minute. Wait a minute. It will become. Okay, so natural. Why half y minus a half if it's so natural for you? Okay, explain. Okay, it's very natural. Half y minus y, right?
Saying that's so natural.
Oh, okay.
That element is natural, but the answer
So
is,
given that half, let
the
me.
answer is that you want to pick up that guy and to
Very good. Very good.
eliminate
Okay.
deviation.
Very good. So keep this thought in mind. Keep this thought in mind because I'm going to use it now. Okay? Keep this thought in mind. So I'm saying paying $50 and getting a lottery ticket that gives you the y goodness probability half, because everything is, as I said, risk neutrality and linear, is equivalent to doing something else. There is a lottery with probability half. You get the good and pay 1. With probability half, you pay nothing and get nothing. It's the same, right? Half y minus a half is 1/2 of y minus 1 plus 1/2 of 0. And everybody's indifferent between those things, the seller and the buyer. So why not replace this thing by those two things, y minus 1 or 0, right? We can take this menu item and says with probability half it's this, and with probability half it's that. And I didn't put 2 zeros because, there is no need to put 2 zeros if I already have 1, okay? Now, what happens if I do that? Wait a minute. Can I keep the 5 here? Now what you guys were all saying, no. Because the guy with 3 previously was doing the following computation. 3 plus 3 minus 5 is 1. 1/2 of 3 minus a half is also 1. So I'm indifferent between those two things, and doing a tiny epsilon perturbation, then you give a delta discount. In fact, that's what all you need to do. Then he prefers that, which means the 5. But now the 3 guy has an option y minus 1, which gives him 2. Since he has an option that gives him 2, y minus 1 is now 2, you cannot charge him 5 here. You can only charge him 4. Right? You have to lower what you charge here. By the way, so when you look at the virtual valuations, that's exactly the same computation you do there. When you increase something here, then you have to compensate this by lowering what you can get from the higher value guys. And that's exactly the epsilon that you add to valuation x influences how much you can get from valuation y, which is bigger than x, and that's exactly this effect, precisely. Okay? So if you want all the hidden virtual valuation is here. Yeah? Very good. Now, so here you are getting less. So here, when you throw this away, you should be able to charge more because he has now no way to run to y minus 1. So how much can you charge here? You should be able to charge 6, which will exactly average out. But wait a minute. There is the option z minus 2. So he can get 1 from z minus 2. So you cannot charge him more than 5. That's the most you can charge him because this pins him down. Now, if we would not have z here, this argument would be beautiful and say this will be a 4, this will be a 6, and then this thing will be exactly the average of those two things. If you want, that's another proof of the Myerson result. Okay? And if you want to understand this, okay, sorry, let me finish. However, here, because there is another coordinate, and there are incentive constraints going in another direction, when you take this random outcome and you decompose it into an average of pure outcomes, the payment does not decompose accordingly because of those additional incentive constraints. And that's why this thing, which is an average of these two, is much better than both of them. Each one of them gives you 2 and a third, this gives you 2.5. It's strictly better, and it's a unique optimal mechanism. Now, if you want to understand this and why a little more, and why is it that only appears when you have two goods, I recommend that you look in the Hart-Rennie T 2015. You have a link in the presentation, and there we spend 1 page or more to really explain why this phenomenon appears when you have only two goods or more. Because the question is, why is it that for one good we never have randomizations, but we do have when there are two goods or more? Yes?
Are there for two goods ever more than 4 menu items for the optimal menu?
Keep this in mind. I'm not going to answer to you now, but I'll give you. But you'll get an answer by 1 o'clock. And if not, ask me again. But you will. Okay. So here we put a price on lotteries, which again, you know, for the national lottery system sounds like a good thing. You know, do good advertising for them, but that's life. Okay. So as I promised, there is a 4 prime, which is things are IID. So that example had nothing to do with correlation, but it was easier to see what's going on rather than this example where you have 9 outcomes and you get lost a little. I think, again, examples where you have randomization exist in the literature. In fact, I have a slide that says it. So, okay, here is a slide. Sorry. Okay, so that's optimal mechanism. Here, again, you see the lotteries. So, summary at this point, to maximize revenue, you can post the price for each good separately. You can post the price for the bundle. You can do both things simultaneously, or you can, the most general thing, post prices for various lotteries. And here I think, yes, here there is a list. So it starts with Stanasulis, and there are lots of papers where you can see examples of randomizations being needed. Okay, of course I'm partial to this one, and the reason is that all the others are computations. And you look at them, and there is a computation showing you that this is better than that. From my point of view, I think that the example that we show explains what's going on, at least in some respect. Why randomizations really matter? Well, it's a matter of taste, but okay. Okay, next. In fact, when I started working on this with Phil, we said, okay, let's work some simple cases to get some intuition on what's going on before we attack the big problem, which is quite difficult, okay? So let's start with a very simple case where we have K uniform 0, 1 goods. IID. Okay, so good 1 is uniform on 0, 1, good 2 is uniform on 0, 1. So if you want, it's a uniform distribution on the K-dimensional cube. Okay? Okay, so K equals 1, we know the solution. In fact, I solved it when I started. Uniform on 0, 1, the optimal price is a half. Right? That maximizes, it's P times 1 minus P. Okay, remember? Very good. K equals 2. This is the unique optimal mechanism. Okay? Well, nowadays probably you should be able to do it in about 3 pages of computations. Originally it took us 10 pages to compute to prove that this is the unique optimal mechanism that says the following. What does the buyer get? Well, what are the choices of the buyer? 0, always a choice, stay out, individual rationality if you want. Pay 2/3 and you can get any single good. So you can get good 1 for 2/3 or good 2 for 2/3. Or you can get both of them for the number 4 minus square root 2 over 3. Exactly. Okay, that's a number. That's what comes out. Okay, I'm sorry, but that's the unique optimal mechanism. Okay. Okay, so once we solve that, let's go to 3 goods. Oh, we did 3 goods. Okay. I won't tell you how many pages. I think the last lemma we never proved, but here is the result. But I'm going to say more than one. I'm going to say more than one word, Elhanan. Wait. You won't like the words I'm going to say, but I'm going to say them nevertheless. So don't push me. Okay, here is the solution. Here is the unique optimal mechanism for selling 3 independent IID goods, each one uniform on 0, 1. What can be simpler than such a question? How do you maximize revenue when you have a buyer that has 3 goods, each one is uniform on 0, 1, independent of the others, right? So here is the unique optimal mechanism. Okay, options. Nothing. Pay 3/4, get good 1. Okay. By the way, see, 2/3, 3/4. There is a series here. That's easy. Pay 3/4 to get any one good. So in fact, this is the short for saying x1 minus 3/4, x2 minus 3/4, x3 minus 3/4. Or you can pay 6 minus square root 2 over 4 for any 2 goods that you want. Or pay S for 3 goods. And you wonder what S is. This is S. I mean, it's quite clear, right? This is clear that is the right price on the bundle. Okay? I mean, who can doubt that? Okay? Who can doubt that? Okay? Now you're wondering where this comes from. Well, that's Maple's way of solving an equation of third degree with coefficients in q square root 2, rational numbers with square root 2. Okay? Now, that's not the only way to write it. That's how Maple wrote it, and I liked it, so I put it here. Yes, you can do it with lots of third roots and so on, but I think that's a nice thing, especially if somebody hires you to tell them how to sell goods, and you tell them that's how you sell the goods. Okay? I hope you keep your job at the university still. Okay, so what do we learn from this? Okay, now, by the way, that's a monstrosity too. I mean, just to solve this thing is really difficult. And what we learned is that we learned lots of things here. Particularly, that's not the way to go. Yes, that leads to really monstrous things. One can characterize those things, but they are terrible. And in fact, nowadays, so there's been some advance here by computer scientists, Koutsoupias and his student Giannakopoulos. This is not John Giannakopoulos. For those who know, this is Giannakopoulos. Okay, most of you don't know what I'm talking about, so there is only one name. This is the name. Okay, and then there is a paper by Kostis Daskalakis, Deckelbaum and Samos, just appeared in Econometrica, very beautiful. So this paper succeeds in solving this problem up to k equals 6, and that's it.
Which one?
Uniform IID,
Which paper?
Giannakopoulos and Koutsoupias,
Okay.
and that's it. At 6, this breaks down.
And what did these guys do?
They do something that includes part of these results, and they have a nice duality, very nice duality characterization of what's going on, which in some special cases gives you result. In general, it's a very difficult problem. Okay.
What do you mean it breaks down beyond
Their method breaks down. No. Mechanism design is there to stay. Sorry, no. There is an optimal mechanism, just we don't know what it is. For instance, we don't know whether it's so. In fact, there is even a nice characterization of what happens up to 6 goods. It's still pure. It's still deterministic. You don't need randomizations. Nobody knows if for 7 goods you need randomizations or not. For 7 IAD uniform goods, you need randomizations or not. Okay. It's only up to 6 goods that their method works, and it's quite difficult. And I had a student trying to look at this and try to. It's not easy to go beyond 6. There is something happening in the geometry there that didn't Zelten have 4 is few and 6 is many? Had a paper, Reinhard Zelten, on competition. 4 is few and 6 is many. Okay, that's another case where 7 is many. Yes.
Is there any hope to have a more simple or easy to compute or reasonable solution to this problem by trying to look at sort of classes of correlations over the objects?
Can you keep this in mind? Can you keep this thought in mind? It's a good thought. Yes, that's why I want to keep you in mind. Yes. Okay, so.
What happens if you discretize the uniform, like each epsilon, then you can use the order method?
Yes, and you're going to get a monstrosity. I have a slide for you on that. Wait. So let's put this on the back burner. Let me now show you another issue, and then we'll continue. Monotonicity. Now, you have all heard here, monotonicity is a crucial thing in mechanism design. So in particular, here is one crucial monotonicity. When the value of the buyer goes up, his probability of getting the good goes up. Okay? In fact, sorry. Okay, we saw that. Who was talking about? I forgot. I had so many lectures now. I forgot. But we saw this at least twice. Even in the small number of lectures I was sitting here, I saw it at least twice during the summer school. And what happens if the buyer now? Suppose that the buyer values the good higher. Previously, he was valuing it at 7 and 9. Say 10 and 22 is probability half-half. Now maybe he values it at 11 and 27 is probability half-half. So his valuation goes up. Okay. Clearly, the seller is going to be able to extract more from a buyer because it's worth more to the buyer. Now, if you want a formal proof, it's a good exercise, by the way, but here is the proof. It's just incentive compatibility. There is nothing. There's really a triviality. Yes, more or less, you have seen those things, so I'm not going to bother you with. The probability of getting the good when your valuation is x prime bigger than x is higher, and so also the payment to the seller is going to be higher. Okay, that's quite a triviality. Okay, very good. So what we have shown, what can be shown very easily, higher valuation means higher payoff to the buyer. Sorry, higher valuation means a higher payoff of the buyer to the seller. Seller gets more revenue. That's true for any mechanism that is incentive compatible. Okay, so it's clearly true when we maximize over incentive compatible mechanisms. So the revenue is always going to be monotonic with respect to the buyer valuations. Okay, One good, very easy exercise. By the way, if you teach that, that's a very good exam question. You know, not too difficult, but still shows that your kids learn something. Okay, how about k bigger than 1? So let's extend this proof. Now instead of extending, I'll show you a picture. Okay, here's a picture. So now I have two goods, y and z. Remember, I call the goods instead of x1, x2, y and z. Consider this mechanism. What is this mechanism? Says the options are 0, as usual, pay 10 and get y, pay 20 and get z, pay 40 and get both. Then I can draw on the plane all the valuations. I can divide the plane into 4 regions according to what the buyer prefers in each region. So in this region, he prefers 0. Here, he prefers to get the y good and pay 10. Here, he prefers to get the z good and get 20. Here, his valuations are very high. He prefers to get both and get 40. And you can easily compute the equations of this line. It's exactly here. This is the line where y equals 10. This is z equal 20, and so on. So those are the 4 regions. Okay. Okay. So let me. You don't have to. You don't have to. I drew it for you. Okay. So consider the green point, and the red point. Okay. You see what happens from the green point to the red point. Both valuations, both goods are worth more to the buyer, right? Because the y coordinate went up and the z coordinate went up. Now, what does the buyer do? In the green point, he was buying the z good for 20. So the seller was getting 20. Now, he's buying the y good for 10. The seller is only getting 10. So the revenue of the seller went down. Terrible. So probably this is not an optimal mechanism, right? That's what you would say. Well, I'm sorry to tell you, I can make this into an optimal mechanism. In fact, I can make this into the unique optimal mechanism for a certain distribution. In fact, for a neighborhood, it's not any for a robust set of distributions, for an open set of distributions. This is going to be the unique optimal mechanism. So think about it, that y goes up, z goes up, nevertheless the seller gets less. And that happens, okay, so what I'm saying is there exist two good valuations, just a second, for which this specific B maximizes revenue, okay? So it's a unique maximizer. I say it's robust even if you perturb the distribution, okay? Everything is restricting inequalities over there. It's a unique optimal mechanism, okay? So what the conclusion is, there exist two good valuations where the valuation goes up and the seller gets less money. Now that sounds extremely strange, okay? Now, seller should be able to do something about this, right? I mean, he is controlling the mechanism, right? Unfortunately, I have yet to find some way for the seller to get out of this difficult problem, this conundrum, right? You call that. So think about it, okay? The buyer values more. Now, it's a buyer, yes? You have control over the mechanism. You do whatever you want. Well, your revenue is going to go down. So think about this guy that is supposed to advise the seller. Seller says, well, I don't know exactly how much the buyer values the goods, but I'll give you some lower bounds. He values good 1 at least at $1 million with some probability, and good 2 at least at $2 million with some probabilities and so on. So you compute the optimal mechanism there, and you say, well, if he values more, you'll get more. No, you may be getting less, in fact. Okay? And there is no way to overcome it. Other non-monotonicities, for example, you may add the buyer. If you add the buyer, the revenue of the seller may go down. Well, the seller can overcome this very easily. You are a new buyer? Sorry, no entry. I don't sell it to you. So, but here, there is nothing the seller can do to overcome this non-monotonicity. It's built in non-monotonicity that there is no way for the seller to overcome, which is quite disturbing. Because all our intuition that comes, you know, valuations are higher, I should be able to extract more. If you value the good more, right, El-Hanan, I should be able to get more from you. What do you mean I can't? Well, I can't. That's life.
It's disturbing for the seller, not for the buyer.
I know, but no, I think it's disturbing for us that, no? Yeah. Well, El-Hanan, should I remind you the first time I told you this example? Should I tell you how you reacted the first time I told you the example? That's not fair. You have heard this for free.
It's clear.
Okay, good. So I'm very happy because that means that the message has passed across that all our intuition that comes from the one good of this, you know, higher values means more revenue, that's false. That's only true in the one good case. It's a very special thing, okay? So you can do this with IID, everything and so on.
It's not even true in the one good case if preferences are nonlinear. There's an old literature on
For respect to first order stochastic dominance, are you sure? First order stochastic dominance we are talking.
If we're out of the quasi-linear frame.
Yeah, okay, maybe.
Even when you're
Yeah,
self-defined.
okay. I want to see that because you are the first one to say this. So I've been talking about this. Nobody has mentioned this up to now, including all the referees, etc. So if there is something I want to
It's a
know.
point from
Who?
a long time ago.
Okay.
From 25 or
Okay.
30 years ago.
So let's look at that.
Go back to this mechanism looks a bit strange because you see a buyer can first buy.
No, he cannot. No, he cannot.
10 and
They-
then he can buy
No,
Z for
no. The interpretation of this is that you can choose one and only one of these options. If you can choose one and then the other, then of course that's a then that's
unnatural.
no. You are missing the point. No, that's a good question, and let me explain very carefully, okay? If you take that interpretation, that's a different mechanism, what you are talking now, where you can buy one good, then you can buy the second, one after the other. That corresponds to a different B function. That thing is not optimal. That is the unique optimal mechanism, which is you only can choose one of these four options, nothing else. Because I'm taking maximum over all possible mechanisms, including the mechanism who interprets this in a different way. That's not going to give you a higher revenue. It's going to give you a lower revenue. That's a theorem. Okay? Very important. So thank you for the question. You can, I mean, again, remember, you can do whatever you want. I'm telling you what is the maximum revenue you can attain in any way possible. I'm telling you this is 20 here when your valuation is low, and when your valuation is high, it's 15. That's it. I don't care how. You can interpret it any way you want. That's part of the proof and so on. That's irrelevant to the question.
What if you restrict yourself to mechanisms that are
Read the Hart-Rennie, and there are some cases where you can say something good, but they are quite limited. Okay, I want to continue. You're asking, so there is something about complexity. I'm not sure that's the right crowd. Usually for computer scientists, it's a good slide, but let me skip that. Let me skip that. Okay, so what we have learned up to now, okay? When you maximize revenue with multiple goods, many of the results for one good are just false for multiple goods. You need randomizations that were never needed for one good. It's not monotonic, and other things that you can see along the way. It's an extremely complex problem, even if you take very simple distributions. Okay, it's really a hard problem. And so I can summarize it that what we have learned from one good is too good to be true for two goods. Okay, now you can understand the title of my talk. Okay, so remember, most of our intuitions in mechanism design come from one good, and many of them are false when you go to more than one good. So one has to be careful. Okay, so what do we do now? Okay, so then we can ask the following question. Okay, optimal mechanism, that's a very difficult problem. It's very hard to solve it. In fact, it's quite unsolvable, I would say, in many simple cases. So, let's look under the light. Yes, where do we look for the key? Yes, we look under the light because that's the only way we can look. When it's dark, you can't see anything. Okay, I know that's a good metaphor, but so let's ask. Okay, let's restrict ourselves to simple mechanisms and ask how good are they. Maybe they're not so bad. Maybe you can say something useful about them. And simple mechanisms are easy to compute. Okay. So let me give you some results in this vein, and so let's start. Okay, here is result theorem 1. Okay, assume that x1 and x2 are independent and identical distributed. Any distribution. We make no assumptions on, no restrictions on distributions. No hazard rate, or any monotonicity, whatever, any distributions whatsoever. IID. Okay, then we have this thing. Okay, what does it say? It says Rev x1, x2 is the maximum revenue you get from selling both goods, whichever way you want. This is how much you get from good 1. This is how much you get from good 2. So that's how much you get by selling them separately. What does it say? This is at least E over E plus 1, which if you're wondering, it's about 3/4, 73%, let's say, of the optimal revenue. So it says the following. Take any two IID goods. If you sell them separately, you get at least 73% of the optimal revenue. I have no clue what the optimal revenue is. I don't know how to compute it. But I know that if you sell them separately, which is something very easy to compute, you apply Meyerson to each good. In fact, Oh, I'll tell you in a moment. Let me, okay, here, okay. Here is, if I have two IID goods, clearly the optimal posted price is the same for both goods because they have the same distribution. So what it says is that you are taking the optimal one good price and you are posting it for both goods and telling the buyer, look, you can buy good 1 at this price. You can also buy good 2 at this price, which means you can buy any number of goods that you want, 0, 1, or 2, at this price. Yes, it sounds a little more like the store. There is a price per good, which is the optimal one good price, and you can buy either good or both of them at this price per unit. Okay? That guarantees you 73% of the optimal revenue. Okay? You don't have to know anything, and that's a result. Yes?
Is that bound short?
2 slides. Okay? Sorry, now I want to go back. Now, what happens if they are just independent but not identical distributed? This 73% drops down to a half, and in fact, and that's work with Noam Nissan. In fact, there is some improvement here. I'll call this theorem 2.62, and the reason it's called theorem 2.62 is not because there are 61 theorems in between, but because this a half has been improved to 62%. And that's some recent work with Phil. You know, after 5 years, we let all these computer science people try to improve that, and no one succeeded. We decided we have to look at it, and it's terrible. It's quite difficult work. But, you know, we decided that we have to try to see how much we can improve. Well, we got it to 62%. Now, let's see how much. You know what? I want to tell you something about the proof because there is a nice idea there. But before that, let me reply to you how sharp are these bounds. It will come in a later slide. I thought it comes now. The worst we know is 78%. So it's somewhere between 73 and 78%. You know, so there is an example. In fact, a simple example. It's what's called the eco-revenue distribution, where indeed selling separately gives you exactly 78% of the optimal revenue. And we know that no matter what, 73% is guaranteed by selling separately. So this 5% gap is not something that I would try very hard to minimize. That's the right ballgame. So I want to tell you something about this proof. Yes, let me spend a couple of minutes because just I'll draw something. Okay, picture, only picture. Okay. So Y and Z. Those are my two goods, Y and Z. Okay. Suppose somebody gives you a mechanism on the two goods. What I want to do, I want to estimate what I get from the mechanism related to what I get from selling the goods separately. Okay? I want to bounce this from above by some multiple of what I get by selling the goods separately. Okay? Sounds strange now, but bear with me. Okay? So you are given a mechanism. So what I do is the following thing. First of all, I take the diagonal and I split it into two parts. So this is the part where Y, this is Y greater equals Z. This is the part where Y is less than Z. Doesn't matter. One can be sharp inequality if you want. Yes, doesn't matter. So let's look here in this region. Let's take this region. Okay? Let's fix Z here. Let's fix the value of the second good. And let's look at the mechanism, what the mechanism does as the value of the first good changes. So really, I'm going to look on this line. This is a line where the value of the second good is at Z, and I keep changing the value of the first good. Now that's a mechanism that what does it do? My original mechanism. I'm given a mechanism. I start with a given two good mechanism. That mechanism is going, so when I'm here, is going to give me a Q1 of YZ, Q2 of YZ, and S of YZ. That's the probability of getting the Y good. That's the probability of getting the Z good, and that's how much I have to pay to the seller. Right? Hello? Anybody with me? No, I don't know. Okay. Very good. Now, sorry? I take an arbitrary mechanism, not generic in any sense that it represents anything, just an arbitrary mechanism, incentive compatible, of course. Okay. Now, from this, I want to get a mechanism for the good Y only. What do I do? So from this, I'm going to define now Q, let's say Q1 hat of Y. I'm going to define to be Q1 YZ. So I'm going to give to the buyer the Y good with exactly the same probability he was getting before, Well, but he's not getting the Z good because now there is no Z good. So what do? Instead of giving him the Z good, I'm going to give him a discount in money equal to the value of the Z good. So his new S hat of Y is going to be the old S of YZ minus, SYZ minus Z times Q2 YZ. So what I'm saying, look, previously you are paying that, but you are getting Z good with this probability. Instead of that, I'm giving you this in money. So the buyer is completely indifferent between this and that. Okay? Now, easy exercise. If this is incentive compatible, then this is incentive compatible just when I vary the Y here. Because I'm only looking at incentive compatibility on the line, because the buyer keeps getting the same thing. Okay? So that Q hat, S hat, is going to be an incentive compatible mechanism for the good Y. Which means that what I get from this hat mechanism along this line is at most the revenue I can get from Y separately. Okay? Very good. Now, okay, so what I have is this. So now I want to look at the expectation of SYZ in the area where Y is greater or equal Z. So I'm looking at how much revenue I get from the original mechanism. Okay, I claim that this is at most the revenue I get from S hat Y in this region plus, okay, you see, written this way, this is S hat plus this thing, plus the expectation of Z Q2 YZ indicator Y greater. Okay, let's put here big Z because we take expectations. Okay, what I did is I forget expectation. What it says that S equals S hat plus Z times Q2. Okay? In fact, I can even put here equality. That's all I did. It's the same equation, except I put expectations and random variables. Nothing else. Okay? Anybody follows? Very good. Now, this thing, so here I have Y greater or equal Z. Now, this thing, I bound by the revenue of Y, because this is the mechanism for Y. This thing, okay, Q2 is always less or equal 1, because it's a probability. Okay? It's a probability. So this is the expectation of Z times the indicator that Y is greater or equal Z. Let me rewrite this thing as Z times the probability that Y is greater or equal Z. Now, do you know this expression? Let me write it this way with small z. It makes, maybe now you recognize this expression. Do you recognize this expression? Yes? Anybody?
Expectation.
Before, yes, there is an expectation here outside. But before taking the expectation, what can I say about this expression? This is like putting a price of Z to sell Y. So this is no more than the revenue of Y. That's a posted price inequality that says that it's just I don't have to use Meyerson or Riley or anybody's theorem. It just says posting a price of Z is a possible mechanism for selling Y. So it cannot be that Z times the probability that Y greater or equal Z exceeds the revenue. So this thing is bounded by the revenue. This thing is bounded by the revenue of Y. This thing is bounded by the revenue of Y. In total, I get twice the revenue of Y. Okay? Which is, by the way, a nice thing here. The expectation of the minimum here is less than the revenue of the maximum. That's what I proved there. That's a neat thing that you get from this thing. So here, in this area, you get twice the revenue of Y. In this area, by symmetry, you get twice the revenue of Z. So you get twice the separate revenue. So what I've showed to you is that the revenue that you get overall is no more than twice the revenue of Y plus twice the revenue of Z. So selling separately, okay, so divide by 2 gives you at least 1/2 of the revenue here. Okay, that's a proof. Now there are some details there, but essentially that's you get the okay. Oops, what happened? Oh, looks like the battery is out. Okay. Okay. Okay, if you want to see, okay, this is the full proof, but not the full. I mean, this is exactly what I showed you. Okay, so now I think it's a nice idea. Yes, so essentially you take the two-dimensional mechanism, you generate from this a one-dimensional one in a neat way, in the right way, and then you bound things, and you get that. Now, if you take this proof and you now I threw away lots of things here, clearly, and you not try to throw away as few things as possible. That's how you get the proof for the independent and for the IID, and that's how you get the square root E and so on. You are trying to do every estimate to sharpen it as much as possible, but still there is some gap there. Okay, now I want to talk about G4. Okay, what's G4? Well, you know G8, right? Every economist should know what G8 is. Now, I dare you, can you say all the 8 countries without missing one? Now it's G7?
Russia was kicked out.
Russia was kicked out. Okay. Even G7, every time I come up, I'm missing one country. Okay. But you can try. Anyway, I want to talk about G4, and I'll tell you what G4, which is not half of G8. You can guess that, but I'll tell you what it is. So I want to define a concept. Assume you are given a class of, okay, let's see, maybe, okay. Assume that you are given a class of mechanisms, incentive compatible individual rational mechanisms. For example, selling separately. For example, deterministic mechanism. For example, selling as a bundle. I mean, those are simple mechanisms, a class of simple mechanisms. Assume you are given a family of possible valuations. For example, IID, two goods IID, or two goods independent, or whatever, you know. Then I can ask, how much of the optimal revenue is guaranteed when I'm restricted to that class? So I'm looking at the guaranteed fraction of optimal revenue, which is G4 in short, guaranteed fraction of optimal revenue, okay, which is that maximal fraction, alpha. I mean, you should have seen it coming, no? Well, not everybody knows me, apparently, yes. But is that maximal fraction alpha such that any valuation you give me in that class, there's going to be a mechanism in that class that gives me at least proportion alpha, fraction alpha of the optimal revenue, okay? So that says there is always a mechanism that gives me at least alpha fraction of the optimal revenue. Okay, that's a very clear thing. So when I say G4 is a half, then I mean, well, in that class of selling separately, I can get at least half of the optimal revenue. Okay? Well, if you want a more complex formula, this is a more complex formula, but ignore that. Okay, so let me now restate the results in a nice G4 formulation. Separate selling of IID goods, G4 is at least 73%. You are guaranteed 73% of the optimal revenue. For independent but not identical distributed, 62%. By the way, that extends to end buyers very neatly. Not that, the old 50%, sorry. I don't know about the 62%. So here, the Hart and Nissan was 50%. That exactly the same proof extends to end buyers. And the upper bound, as I said, is 78% on all of them. It's just one example that gives 78%. Nobody knows anything better than that. Now, when I talk about end buyers, the nice thing is that this is, just one second, that this is done, this proof is completely transparent to the details, which means it works just as well if you do Bayesian-Nash implementation or dominant strategy implementation, so long, of course, that you do the same for one good as for the two goods, okay? So it doesn't really matter, it's really a general decomposition result that gives you that, okay? So you have to use the same implementation for both. It says selling separately with end buyers, so good one you have one market, good two you have another market, or you do together, well, you are guaranteed 50% in the independent case. Okay. Yes, you had a question.
Can you say anything about a related question about fixing a single mechanism and then varying over some structure class environments?
Yeah, I can say very few things, yes. So there are cases where, for example, you can ask when is bundling good, okay? So there are some results, some special cases. I can point to in the literature. There are a couple, maybe one or two theorems, and that's it, which tell you some conditions where bundling is optimal. But they are, you know, if your example falls in that class, very good. If not, tough luck. So there are very few results like this that tell you that for special distributions this works. There are some results.
What about even approximate optimality, similar to the exercise you're doing, but fixing one mechanism?
Well, that's like looking at, yes. So we are talking about selling bundling. So the class of mechanisms is one interesting class selling separately. I talked about that. Another is selling bundling. So if you look in the Hart-Nissan papers, then you'll see lots of results telling you exactly what you can get by bundling, what you can get separately, what are the comparisons. So there are lots of results like this. And there is, by the way, a whole, this was 2012. So since then, computer scientists have done lots of other things, and there is much more stuff. Okay. If you look on my webpage, by the way, I think that there is a newer version there which has been updated, including references to future work. I mean, future relative to 2012, but present for now. And it's only a sample, but there are definitely much stronger results now. Lots of results. Okay. Now, next, and essentially, probably it's the final. Yes, the final topic I'm going to talk. Let's drop up to now. The two goods, the two or K goods are independent. Okay. And what we got, well, you know, I don't know how to solve the problem, but if I sell them separately, which is an easy thing, I'm guaranteed a sizable fraction of the optimal revenue, and that at least I can do in 2 seconds. Yes, no problem. Solving the problem, you know, even give me 100 years, I don't know how to solve it. Okay, so what's better, you know? Never to sell it or to sell it at 75% of the optimal revenue? Okay, so now assume that we talk about two goods as arbitrary dependence. Okay, so I have two goods, the valuations may be correlated. So the question is, what is the G4? What is the guaranteed fraction of optimal revenue that I get when I sell them separately? Okay? Answer, 0. 0. What do I mean by 0? So I'll tell you exactly what I mean by 0. For every positive epsilon, there is some valuation x, even in 0, 1 squared. Everything is bounded. I'm not working with infinities, such that what you get by selling them separately, SREV is, you know, revenue of x1 plus revenue of x2. SREV is separate revenue, okay? Is less than epsilon of the optimal revenue. Terrible, right? So there are valuations for which selling them separately, you get nothing. It's very bad. Okay, so separate is out. Let's try bundling. How much do you get? 0. Same 0. So there is valuations so that if you sell them as a bundle, you get less than epsilon of the optimal revenue. Okay. But maybe I'm smart. For some valuations, selling separately is bad, but bundling is good, and the other way around. So let's try deterministic mechanisms, which includes separate, includes bundling, and includes also the option of, at the same time, giving prices for the bundle and for these goods. What is G4 going to be? You want to guess? 0. Okay? Okay? So there is a valuation X, so any deterministic mechanism, selling separately, selling bundling, putting prices or whatever you want, but deterministic, is going to give you less than epsilon of the optimal revenue. Terrible, right? Terrible. But that's life, you know. That's how the world is. Okay? And of course, if that's true for two goods, it's also true for any other number of goods. Okay? Now, if you think, so in fact, I can give an example, an actual distribution. I give you a distribution, and I'll show you that what you get by any deterministic mechanism is going to be arbitrarily small fraction of what you can get in an optimal mechanism. Now, why is it that, so that's Hart and Nissan 2013. It's a paper that has in the title menu size. Why does it? Yes, that's what I'm doing now. That's what I'm doing now. I'm explaining it. That's what you want, right? I knew it. Do I know you from someplace? you keep asking the same questions. You keep asking the same questions. No. That I'm trying to explain this. So, menu size. Let's talk about menu size. What's menu size? Well, we understand what menu is. Menu is the number of options you give to the buyer. So, separate selling, what are the options? Nothing. Pay P1 for good 1 or pay P2 for good 2. That's it. 3 options. Bundling, we have 2 options. Yes, there are a number of options. Okay, so let's be large. Let's be nice. Let's look how much revenue you can get from mechanisms that have 100 possible outcomes. M equals 100. So I'm looking at mechanisms that give to the buyer 100 possible options that he has to choose whatever he wants out of those 100. Okay. Sure. Some, of course. I mean, the price for good 1, price for good 2, price for the bundle, that's 3 options. I'm done. All the rest must be probabilistic. Prices for lotteries, okay, if I have 2 goods, okay? So I give you 100 options. Of course, some of them will be, most of them will be lotteries, maybe all of them will be lotteries, okay? How much revenue can you get? Let's call this MREV M, okay? What's G4 for that? I'm sorry to tell you, it's still 0, okay? So even if you say, you know what, It's not selling separately or selling together, which is just 4 options. I give you 100 options. You know what? 10,000 options. How much revenue can you get? Zilch. I'll find a distribution. I'll give you a distribution so that any mechanism that has at most 10,000 options, any mechanism that has at most 10,000 options will give you no more than epsilon fraction of the optimal revenue. Okay? It's quite bad. Okay? Now, just a second. Okay, sorry. No, ask.
Sorry, so this is for the independent case?
No, that's for a correlated case. Because for the independent case, you already know that I get 62% from selling separately.
I thought we already knew in the correlated case that G4 is 0 even if you don't restrict the number of item functions.
No, what we knew, no. What we knew for separate, bundle, and deterministic.
Oh, I see.
Now, of course, if I ask you G4 for stochastic mechanism, what will be G4 for stochastic mechanism? 1, okay, just to make sure that everybody follows. Yes, it's clear. If I allow stochastic lotteries, G4 is going to be 1 by definition because every mechanism is allowed. Okay, so deterministic is 0. Okay, good. So now I say, it's not all possible mechanisms, but only mechanisms that have the number of lottery tickets that you are allowed to buy that are given to you as options is bounded by 10,000. Only those. Only 10,000 lottery tickets. I mean, can you imagine something more difficult? I mean, other mechanisms, I don't know how you can play them. Nevertheless, such mechanisms for some distributions are going to be arbitrarily bad. They are going to give you less than epsilon. Really, what you need is menus of arbitrarily large size to extract the revenue. You may need more and more menu items to extract the revenue. Any finite number of menu items, and no matter what they are, I'm not telling you what they are, yes, it's on any. The moment you bound the number of menu items, that's it. You may get an arbitrarily small fraction of the optimal revenue.
But as M...
Can wait, I think I have an answer for you. Look, I mean, it's a natural. I think if not...
He said the same to me.
You did. Okay, yes, sorry.
You knew what your question was. You know what my question
Yes, but don't you think I asked the same question?
No, it's not the same.
Oh, okay, maybe not. But give me 1 minute just to finish that, and then okay. So as m increases, this increases, of course, because in the limit I get 1. Yes, I get everything. And now a nice thing that comes up here when you look at k goods. So when you look at the k goods, deterministic mechanism has 2 to the power k options. The menu size is of size 2 to the power k, right? It turns out that what you get from deterministic mechanism and what you get from any other mechanism whose menu size is of the order of 2 to the power k is more or less the same. So really, conclusion, the reason deterministic mechanisms are not good enough is not because they are deterministic, because they have too few options. It's a number of options that is a limiting factor, not the fact that they are deterministic. I mean, it's an approximation, but that's a good intuition to have. Okay. So what comes out of here turns out that the menu size is a good measure of the complexity of the mechanism, and you can talk about the menu, about the revenue that you can get as a function of the menu size. But again, I'm out of time, so I owe you that, but let's just put the final slide and then we can discuss. So, summary. For IID goods, 73%. Independent goods, 62%. Arbitrary goods, 0%. That's a picture, remember, okay? That's what you can get with simple mechanisms. And I don't care how you define simple. Define simple selling separately. But any mechanism that has arbitrarily large number of menu items cannot be simple. So if I say simple has to limit the number of options that you give to the buyer, automatically you are in trouble with correlated values. Okay? So, summary now, real summary of everything. Remember what I want you to take home. Many of the results and intuitions for one good are false for multiple goods. It's a very difficult problem. What we have learned from one good is too good to be true for two goods. Simple mechanisms may, also may not, yield uniform approximations. Okay? And I think, right, and that's my, now you can ask your question. Yes, that's my final slide. Yeah. I hope you can read, yes? I'm done.
So, when M is increasing,
how does the revenue increase with M? Is that the question? How does the revenue increase with M?
no. In order to get your G4 equals 0, you're presumably making the distribution itself more and more complicated, right?
I have one distribution that is arbitrarily bad for every m.
The same distribution, you use the same distribution.
Yes.
But
You won't like it because there are infinities there and zeros and so on, but you can approximate its finite things and get anything that you want from that.
But if you approximate it with a finite distribution,
Yeah.
then
You are going to miss.
after m gets
So the point is that, okay, the point is that distribution is going to have countable support. And in each value, you are going to get a positive revenue, but it's a different menu item. And you cannot use any menu item that is good for one value. For another value, it's going to be very bad. So you really have a distribution that has countable many values, and each one has a tailored menu item good for it. Anytime you limit it, is essentially getting a finite sum out of an infinite sum, which is arbitrarily small. That's what really is going on. Okay? But again, those are technicalities. The point is that whichever way you look at it, it's really bad. I mean, this problem says approximating it, yes, this tells you something about the level of complexity of this problem. If all these natural approximations don't work, you'd expect, there will be going to be m that's going to work. No, it's not going to work. Yes, that doesn't matter how you do it. Yes, they're really, really, really complex problems. Okay, extremely complex. Despite the fact that it's a simple problem. I mean, come on. I say to my friends that are doing mechanism design for a few decades, I mean, come on, you don't know how to solve 3 IID goods with 0, 1, uniform 0, 1, and you claim that you know mechanism design? No, I'm, okay, I'm a little, yes, unfair, but yes, okay.
Coming to my earlier question, if we do not have correlation, do you ever need more than 2 to the power of k menu items for the optimal mechanism? Do you know counter example?
That's a good question, and in fact, I may not know the answer, but I think there is some new work by Babayov Nissan, and I think there is some new work that gets the answer to that, but I'm not sure. I'm not sure if we... I don't know, I have to think about it. I think I knew the answer to that, but now I'm not sure. Yes?
So what if you fix the number of messages you allow and assume that the values are all independent? Do you have any bounds on what fraction of revenue you can get as we say let the number of goods be arbitrarily larger than fixed number?
Yes, there are results, and for example, important things there, things grow like the log of the number of goods, but again, some of the things that have been improved, like 1 over the number of goods, or the log, or k over the, I mean, there is a whole literature there, as I said, in the computer science, I can point you out to that, and those things are being improved, yes? I mean, I can't tell you what the state of the art is today, I can point you to where it goes.
Your law of large numbers are usually
Okay, sorry, one thing which I mentioned at the beginning, right, if you have many IID goods, or in fact many independent goods, where you can apply the law of large numbers, then essentially you can get 1 minus epsilon of the revenue. You can subtract. The seller can extract essentially everything. You can get more or less the expectation of the values of all the goods by just the argument that I gave you. Yes, you just give a price to the sum. Yeah,
Doesn't that relate to the bottom point here? Deterministic revenue.
Yeah. No, because that's for independent. For independent, I'm in much better shape. He was asking about independent, right? This is for general. In independent, deterministic mechanisms are much better, namely bundling. When you have a huge number of goods, bundling, you get everything you can ever get. You get 1 minus epsilon of the optimum. The bar gets essentially 0. More than that you cannot get, so you are in a perfect, nice world. Okay? And then I don't need all these things. These things, I need them for the correlated case. So that's a good point. Yeah.
Okay, thank you.